Okay. Okay. Let's get started. So, please check your attendance on the blackboard. So, as I mentioned, this is the in this course we you need to check your attendance by yourself on the blackboard. Okay. And then actually the previous class some students asked their attendance, but I cannot verify the system. But so we check the system. Okay, so what did we learn in the previous class, guys? So we learned about the power consumption issue of processors, right? So the CPU is the system, and then we can deal with the systems using semiconductor technology. So which means that we can build electrical circuit, that's the circuit. And then on the electrical circuit, electric current flows. So which means that obviously electrical circuits consume power, right? Okay. So we learned some dynamic power consumption equation. It's like this: the power is proportional to the capacitive load. So the capacitive load is also proportional to the area of a chip. Okay, the area of an eye, and then the supply voltage. Then this capacitive load is multiplied by the square of supply voltage, and then we can also multiply frequency. Okay, frequency actually defines the activity of electric circuit. So and then also we learned about the Dennard scaling. Then I mentioned that the semiconductor technology is the very critical technology on CPU industry. Actually, but the semiconductor technology is very important for the industry of nations. So, and then we discussed about the Dennard scaling. So Dennard scaling means power density. So we can reduce the size of the transistor with the advanced transistor semiconductor technology, and then Dennard scaling means that with this transistor scaling, that we can reduce the size. And then also I mentioned that if we can reduce the size of transistors, then the characteristics, such as the performance, that is related to the execution time. We can improve the performance. Also, we can reduce the power consumption by reducing the supply voltage to the CMOS circuit. So, because of these narrow characteristics of advanced semiconductor technology, the good thing is that the power density. Power density is the power consumption divided by area, the area of a die chip. So you can say that the power density stays constant with the scaling of a transistor. Okay, that is the Dennard scaling. So which means that if the transistor technology is advanced, then we can use narrow chips without consuming more power. Okay? But in reality, actually, recently, around the 2006 or 2008, the Dennard scaling already has ended. Okay, so which means that this graph shows the red line shows the size of transistor, right? Actually, the width of the transistor channel, and then this blue line shows the power density. then we can observe that the power density is increasing continuously. So it means that the recent chip, modern CPUs will consume more power or much power. Okay? And then because of the power issue, we are using the multi-core architecture. So which means that a single chip, a single CPU includes multiple cores. The core is the independent processor. Okay, it can execute the independent threads or process. So with the multi-core architecture, we can increase the throughput or latency. Throughput or latency. Throughput, right? The amount of work done in the unit time. So with the multiprocess architecture, I mean the multi-core architecture, we can increase the throughput of our computer system. Okay, and then as we learned, we can use benchmark applications to measure the performance of a computer system. Then I introduced about the spec benchmark. It's a very popular benchmark application for CPU. So we briefly explore the characteristics of power consumption by the amount of workload. Okay. So and then now, so in this time, so I will briefly introduce about Moore's law. The Moore's law is a very important law in the CPU industry or chip industry. And then I will briefly explain about the instruction set architecture of computer system. Okay, so what is Moore's law? Actually, Moore's law is, as I mentioned, the Moore's law is very important and very popular law in semiconductor industry. So it's a law, it's called a law, but it's not a scientific theory, or it's not a scientific law. Okay, like F equal ma. So we can say that this is the it's a physical law. But Moore's law is different. So Moore's law is actually empirical observation. So which means that actually the Gordon Moore is the Gordon Moore was Intel's CEO, and then he observed the some trend in the semiconductor technology or CPU industry, and then he observed that the number of so I need to show this. He observed that the number of transistors, not performance, okay, the number of transistors doubles, okay, doubles every 2 years. So which means that, so actually he observed the number of transistors within one CPU, and then he found that just the number of transistors, the number of transistors increase by double every 2 years. That is the Moore's law. And then I also said that this is an empirical law. It is based on the just observation, not a theory, not a equation. Okay. Then why Moore's law is very important? I said that Moore's law is very critical and important in the semiconductor industry or CPU industry. So this is the Moore's law. In the Wikipedia. So actually he died this year. Gordon Moore was CEO of Intel, so he was a co-founder. Why Moore's law is important or critical? And then recently we said that we are saying that the Moore's law is empty. Okay, but I said, oh, this is very important law. Why? So actually, so Intel is the very famous CPU vendor, the CPU company, and then actually Intel has developed their semiconductor technology based on Moore's law. So which means that I said that the size of transistor is decreasing by year. So which means that we can develop narrow transistors using the advanced semiconductor technology. But Moore's law just explain the trend of this semiconductor technology, and then based on the Moore's law, the fabrication company like the TSMC or Intel, so those are very famous semiconductor company, they can set a technology goal. They can set a technology goal based on Moore's law, right? So which means that they can develop, also they can build some development plan for their next generation CPU based on the expected advances in semiconductor technology. Okay, that's good. Which means that in other words, I can say that we can say that Moore's law, the Moore's law. Oh, I think this is about the Moore. So Moore's law just help us set a goal for developing next generation or better CPU. Okay, so we can just expand advancement in semiconductor technology based on Moore's law. Okay, so in this graph, so this graph shows the y-axis. You can find the transistor count. It is the number of transistors per chip. Also, we can observe that this is log scale, right? And then the x-axis represents years. Okay, and then we can also observe the linear, the So we can observe that the number of transistors is increased by year for each trend. So we can observe this is a linear graph, and then the y-axis is the log scale, which means the number of transistors per chip has increased exponentially. Okay, actually More just expect this trend of the transistor density in a chip. And then also we can observe that the Moore's law has continued until 2018. Okay, so I think the mic doesn't work. Sorry. Okay. So it means thanks to the advancement in semiconductor technology, and we can develop a better CPU based on Moore's law. But the trend is changing. Actually, I said so. This graph shows the actually many different statistics, like the number of logical cores per chip is the black color, so number of logical cores. Okay, and then also this red triangle shows the typical power per chip, and then the green dots represent clock frequency of a chip, and then also you know the blue dots represent a single thread performance. Then this color, the orange triangle represents number of transistors per chip. So we can observe that based on Moore's law, number of transistors has increased exponentially, right? It's exponentially, you know, the y is the low scale of CS. But we can observe that actually the power has increased until the early 2000, but it is saturating. But we can also observe that recently the physical power is increasing, right? It's increasing because the recently, so you know, the clock frequency is saturating until the 2020. But recently also Intel and AMD are increasing their clock frequency. So, but power is also increasing. So single thread performance is saturating. So we can observe that CPU vendors have increased the number of cores per chip. So also by increasing the number of cores, the Moore's law has continued. But recently, it's very hard. It's very hard to develop barrel transistors. So we can say that the Moore's law is ending. Okay, so that is actually the very critical changes in CPU industry. Also, the very critical changes in computer systems, right? So this graph shows the Moore's law in DRAM, the memory. So you can find that. The Moore's law is so the testing. The number of bits per DRAM has increased exponentially, but the trend is so also the density is being saturated. So Intel processor, this is the Moore's law, but you know, the work actually the gap between Moore's law and the real CPU is continuously increasing. So which means that it's very hard. It's very hard to change the trend, actually the expectation of the Moore's law. Okay, and then I said that this is the very big change in computer systems. Okay, why? So I said that everyone wants barrel computers, right? And then actually not to build barrel computers, then so we require barrel semiconductor technology. And then Moore's law says that with the barrel semiconductor technology, and we can build barrel CPUs easily. It's not easy, but so which means that we need to develop very advanced technology in semiconductor and architecture. But based on these advances, so we can use barrel computer or barrel CPUs or barrel processor. But this trend is ending, which means that we may need to change the basic structure of our computer systems, right? So this environment is being changed recently. Okay, but in this course, this is the undergraduate course, so I will explain the basic structure or basic architecture of computer system. But this is a very classical knowledge. Okay. So this slide shows 8 great ideas in computer architecture. So for a day, the design for workflow, so which means that we can design use based on workflow. We can set a development of we can set a goal for development of CPUs based on workflow and use abstraction. I already explained about the abstraction in computer systems, right? So we can use abstraction to simplify design. So this is very critical technology or critical approach for understanding very complex systems like computer systems. And make common case best. Okay, so this is a great idea to develop a velocity to make the common case best, and then so this is related to the instruction at ISA, and then performance can be improved by parallelism, parallel processing, or parallel execution. Okay, so we can increase performance via parallelism. Actually, we will not learn about this. So we learn about the instruction level parallelism, but actually this parallelism can be some core level or thread level parallelism. But you can understand, you can think that using a parallel execution or parallel architecture, we can increase the performance, especially throughput of a computer system. And then performance can be improved by pipelining. So I said that this is a very important concept in computer architecture. So we will learn about the pipelining in chapter 4. Then performance can be improved by prediction. Then hierarchy of memory. So we will learn about the memory hierarchy in chapter 5. Okay, and then this is the reliability issue. So these are 8 great ideas in computer architecture. So based on these ideas, so we have developed a better computer, or better computer systems, or better computer processors. Okay. Okay. So this is the end of chapter 1. So I hope you can read the textbook, the chapter 1. Okay, so we will move on chapter 2, instructions. Okay, in chapter 2, we will learn about instructions of computer, which means that instruction set architecture. So in the title of this chapter, so we can find that what are instructions? Instructions are language of computer. Okay. So you may think that we already know programming languages. Then using these programming languages, we can write code. Okay, we can build applications, and then these applications can be executed by processors. But actually, so I said that the processor CPU are digital systems, a kind of digital systems, and then actually the digital systems can understand only digital signals, and then digital signals are very different from our natural languages or programming languages. Okay, so which means that these languages need to be translated to the language of the computer. Okay, so in this chapter, we will learn about the instructions for RISC-V processors. Okay, okay, let's start. So I said in chapter 2, we will learn about instruction set architecture. It's also it is called ISA. Okay, ISA. So it's called ISA. Then, what is an instruction set architecture? So, in this figure, you can find hardware, and so you can find software. So, what is this? What is this human doing? So, the uh, hardware is lifting a large plane. Okay, so actually hardware is the playground of software. And then the software, the two people are playing each other. The hardware. And what is on instruction set architecture? So you can find this plane is instruction set. So it represents the instruction set is on interface between software and hardware. So I said that this hardware, the hardware is a computer system, the computer processor. The main part of hardware is a computer processor. And then a computer processor cannot understand our programming language. So which means that hardware, a computer processor only can understand the instructions, the defined instructions. And then the hardware can execute defined instructions only. So for software, because these instructions are low-level languages, it's very hard to understand these instruction sets. Also, it's very hard to develop applications using these instructions. That's why we are using programming languages. So, based on this interface, software, the high-level language code is translated and into the languages it can be understood by hardware. Okay, so this figure shows the relation between the hardware instruction set and software. Okay, hardware is here. So I will explain the instruction conceptually using this figure. So, what can you see? So in this figure, you can see the rectangle, and then this rectangle represents a processor. A processor receives what? A processor receives instruction. And then, what is the output of this box? So input signals are instructions. So a processor receives instruction, and then processor generates output. Then what are outputs of this process? So change of state. What does it mean? Change of state. So instruction, then what are instructions? Which instructions are given to a processor? So these are examples of instructions like the arithmetic or logical instruction, and then data transfer or control instructions. So for example, plus 1 plus 2 and 3. So actually in real world, we frequently use operators, the arithmetic operators such as addition, subtraction, multiplication, or division. And then actually this is an example of an instruction. But what does that mean? We can define arithmetic instructions such as add. Okay? And then actually in the real world operation, operators require data like 1 and 2, and then these data are called operands. Okay, this is operator, and then is a operand. So using operator and data, operands, then we can calculate output of this operation, right? So some instructions of a computer is similar to this operation. Okay? Processor receives arithmetic instruction such as add instruction or sub instruction or logical instruction like AND instruction. Also, we can give a data transfer instruction. So we will learn about the data transfer instruction later. And we can also give other type of instructions to processor. And what are outputs of is input. So I said that outputs of this process is change of state. What does that mean? So 1 plus 2 generate 3. Okay. So actually, state in a computer represent data. And then actually the data are stored in memory components. Okay. So which means that the change of state means the data stored in memory components are changed by instructions. Okay. So what does that mean? So actually, we can define instructions of a processor or of a computer like the AND. And then if this AND instruction is executed by a processor, then processor changes state. It's state like actually the processor changes the data stored in memories. Okay, so instruction just defines this change. For example, and x1, x2, x3. So this is the example of RISC-V instruction, and then actually this add instruction requires 2 input operand like 2 different data, and then performs x2 plus x3, and then store this data to x1. This is x1. So add instruction changes the data in x1. Okay, you understand? So you can understand like this. A processor receives instruction, and then when an instruction is executed by a processor, the processor changes state. It means the data in memory. So if we define the behavior, so what is the behavior of this example? So what is the behavior of this add instruction? Add instruction read 2 different data in x2 and x3, and then generate result. So performs add operation, and this result is stored in x1, which means this result changes the data in x1. So that is the definition. So I said it's a definition. So based on this definition, a processor changed the state But actually, based on this instruction, processor just changes data in register files and main memory. So actually in chapter 3 and then chapter 2 and chapter 4 and then chapter 5, so we learn about the many different components in processor. And then you can find the also different levels of memory components in a processor, such as the register file, caches, or main memory. So actually there are many different components in a processor, right? But when an instruction is executed, this instruction just changes data in register files or main memory, right? You need to understand this. So this is the concept of executing instructions. So in summary, the instructions are given to a processor, and then a processor generate a change of state. So it means that the data in memories are changing. But only the data in register file or main memory can be changed by instructions. So instruction, what is an instruction set architecture, like ISA? So like this is the ISA instruction. Then what is an ISA instruction set architecture? So in this example, I just show an example of add instruction. But you can also imagine other types of instructions such as subtraction, multiplication, and division. Also, you can imagine some logical instructions such as and, or, exclusive, or. So what does that mean? There are many instructions. So we can define many instructions that can be executed by a processor. Then we need to define the behavior of these many instructions for a processor. This processor. Then instructions and architecture mainly mean a set, a group of instructions. So which means a group of defined instructions for a certain processor. So this is the meaning of instruction set architecture. Okay. But also instruction set architecture defines some architectural behavior, which means that instruction set architecture also defines the number of registers or some size of maximum memory. So instruction architecture, as I mentioned, it is also represent a collection of instructions. Okay, and then also instruction architecture includes some architectural view of the memory registers and then also number system, something like that. Then, so actually, recently, currently, x86 and ARM ISAs are very popular instruction set architectures. Then what does that mean? That's x86 and then ARM ISA. So so recently Apple is a very popular vendor, popular hardware and software vendor, and then they changed their CPU from x86 architecture to ARM architecture. What does that mean? x86 or ARM. So the ISAs are different. Then it means definitions of instructions are changing. So what does that mean? So we can define many different instructions by this instruction set architecture, such as the for the x86, the add instruction like add R1. Well, so there can be many different instructions like add R1, R2. And then for this ARM architecture, then we can define the add R1, R2, R3. Okay. So just definitions of instruction are changing. So, and then the hardware can be designed based on these definitions for this policy. So what does it mean? x86 hardware is based on the definition in x86 ISA. Okay, and it just supports the instruction defined in x86 ISA manual. Okay, and x86 can understand add R1, add R1, R2, but it cannot understand the ARM instructions like this. So it's the same for the ARM. The ARM architecture, ARM processors cannot understand instruction in x86 ISA because ARM processors, ARM hardware, ARM processors are designed based on the definitions in ARM ISA. Okay, so it's a different language. So x86 processors cannot understand the instructions of ARM processor, ARM ISA. Also, the ARM processors cannot understand the instructions of x86 ISA. Okay, so this is the difference. Also, we can be confused with the micro architecture of a CPU. So what does that mean? Based on the ISA, we can design different types of CPU, such as Intel Xeon and Intel Celeron. So Intel Xeon or Intel Celeron just support x86 architectures. So what does that mean? It's a binary. So let us assume that we have a binary file like the GCC. And then GCC binary is compiled using x86 compiler. And then I said, so Intel Xeon and then Intel Celeron supports x86 ISA. It means the GCC binary file compiled by x86 ISA can be executed by Celeron. Because Xeon and Celeron both support the x86 ISA, so which means that both processors can understand these instructions in x86 ISA. So which means these same binaries can be executed by both Xeon and Celeron. Because Xeon and Celeron support x86. But microarchitectures of these two CPUs are different. So what does that mean? Microarchitecture just represents the hardware architecture. Hardware architecture inside of a CPU core. So we can say that Xeon is a very powerful CPU, but Celeron is not. Celeron is the low-end CPU. The performance is very low compared to the Xeon. It is because the hardware design is different. And that this hardware design can be defined by microarchitecture, that architecture. So microarchitecture of the CPU design. So microarchitecture can be defined, but if the two different processors support the same ISA instructions and architecture, then it means it can both processors can execute a binary file compiled by the supporting ISA. Okay, so do not be confused with the microarchitecture. So Xeon Celeron can execute the same binary file, but the performance can be different by microarchitecture design. Okay. Okay, so what is the instruction set? Instruction set is just a repertoire of instructions, the list of instructions. So as I mentioned in the instruction set, the behavior of different instructions are just defined. Add, subtract, multiply, or division, or and or instructions. Okay. So, and then also when we design an instruction set, then we can also follow some popular policy, the design policy. It's not a rule. So I will explain about these design policies for instruction sets. Okay. And then in this course, we will learn about the RISC-V instruction set. So as I mentioned, the currently our instruction set and there is this instruction set, popular instruction set. But in this course, we will learn about the RISC-V. Okay. So RISC-V was developed and used locally, and then also the important feature of RISC-V is the open ISA. What does that mean? So actually, the x86 was developed by Intel, and then RISC was developed and managed by ARM. And then these are very famous CPU vendors, and then these are commercial vendors. So which means that in order to use x86 ISA or ARM ISA, then the companies need to pay royalty to these companies. Okay, it's not cheap. So, but RISC-V instruction set were developed and used locally. And then it's also an open item, which means that hardware vendors need to pay royalty to this for this use locally for using RISC-V instruction set. So currently, many companies such as Samsung, Hynix, and then some other venture companies have interest in using RISC-V ISA. It is because in order to use x86 or ARM ISA, so they need to pay royalty to Tom or Intel. But RISC-V is different. This is the open source ISA, so we don't need to pay any royalty to this locally one RISC-V foundation. Okay. So, and then RISC-V instruction sets are managed by RISC-V Foundation. And then, this ISA was developed recently. So usually this ISA is very clean. So it means actually, the x86 has very low history. And then actually the Intel has added many instructions. And then it makes x86 very complex ISA. So it's very hard to support all kinds of instructions in x86 ISA. But the RISC-V was developed recently, and it has a rather clean state. Okay, so which means that the RISC-V includes the fewer instructions, and but we can build software using the fewer instructions. Also, it is easier to understand the structure of instruction. Okay. So if you want to know about the RISC-V ISA, then you can click the slide or the video. Okay. Because you can find some design strategy of RISC-V ISA. And then, so as a background, I briefly explain about I briefly compare the RISC-V to the two popular ISA, like such as x86 and ARM. So, x86 ISA. Actually, the x86 ISA is called the ISA of CISC. So, what does that mean? What is CISC? C means complex. And then I means instruction. Set, C means computer. It's CISC. So based on, actually x86 is the CISC family. So which means the ISA is very complex. Okay. So then it means the structure. The structure of these instruction set is nothing but pattern. So it's not free, it's a commodity ISA. Then there are around 1,300 instructions. Okay. So there are many instructions. And then this is the size of the instruction set up to the manual. It's about 2,900 pages. Okay, so it means actually it means the x86 ISA is very complex ISA. It is because the x86 has a long history, so it has the 8-bit instruction, also it has the very low instruction. So the instruction length is the 1 to 15 bytes. Okay? So it is because of the backward compatibility, Intel has added the new instruction. But the Intel hardware also needs to support old instructions also. So that's why the x86 includes any instruction that is also very complex. And then ARM. ARM is the RISC family, like RISC. So ISC is the same instructions and computer, and ARM is the reduced. So it means ARM is simpler. ARM ISA is simpler than x86 ISA. That's why ARM ISA is good for mobile processors. Okay? Because the ISA is simple and you can design simpler hardware decoder. And this decoder will not consume much power compared to the Intel decoder. That's why we use ARM for the mobile processors, but ARM ISA is not free. Also, it includes the 400 instruction and the big instruction set architecture manual. And then RISC-V is designed for research, education, also for commercial use. Then features is a kind of a design goal of the RISC-V ISA. It's simple and then clean state. So currently clean, but we can add more instructions. RISC-V also, then it can be complex also, but currently it keeps clean state. Okay? Also, another feature is the RISC-V is the modular ISA, which means we can add more features in RISC-V ISA. So let's see the example. RISC-V ISA is composed of base instructions and extensions. So base instructions of RISC-V ISA is the integer instruction. So what are integers? What are integer instructions? What are integers? In Korean, integers 뭐죠? 정수. So actually the base instructions of RISC-V ISA are integer instructions. Okay, so also RISC-V supports the 32-bit instruction and 64-bit instruction. So this number represents the bit 32-bit computer instruction or 64-bit computer instruction. So base instructions for 32-bit computer is the RISC-32I. So I represents integer instruction. And then for 64-bit computers, the base instruction set is the RISC-64I. Okay. So is a popular base integer ISA for RISC-V. Also RISC-V supports the 32E. There is the number of registers is just 16. But actually the default instruction set is the RISC-32I for the 32-bit computer system, and then RISC-64I for the 64-bit computer system. And then in this course, we will focus on the RISC-32I, the integer instruction set of 32-bit computers. Then the baseline. The base instruction set includes only 50 instructions. So very small number. Okay, compared to the ARM or x86 instruction set. Also, we can include some extensions to support the more instructions. So M represents the integer multiply and divide, and A atomic, and then F. F represents the single precision floating point instruction, which means 4 byte. It supports the 4 byte floating point numbers. Okay. And then E means the double precision floating point is the 8 byte. It supports the 8 byte floating point numbers. Okay. And then G represents the general purpose, and G includes the integer, multiply, atomic, floating point, and double precision. Single precision and double precision floating point. So usually for the general purpose processor, we use the RISC-32G. Okay, G represents the IMAFE. So if our processor supports the RISC-32IM, so which means that this processor supports integer instruction of RISC-V and integer multiply and divide instruction of 32-bit RISC-V instruction set. Okay, so this is the feature of RISC-V ISA. So the RISC-V ISA has the base integer instruction sets like I. So we can add more instructions using extension. Okay, this is just a table that compares the ARM and RISC-V. Why ARM? Because the RISC-V is also RISC type ISA. So as you can see, the name represents RISC, RISC. Also, ARM is the RISC family. So ARM is also RISC type ISA. And then it's actually in this figure, the instructions are just compared. Okay, the instruction size, Also, you can find the reference card on the RISC-V. So I will upload this reference card on Piazza, the resource tab, the Piazza, and then on this reference card, you can find the name definition, actually the name of one instruction. So you can find the format. We learn about the format also. And then this is the example of structure of an instruction. Okay. So as you can see, you can find the multiple instruction. So this is the part of RISC-V. So this is the RISC-V 32-bit integer instruction. So each row represents a separate instruction, right? It means in this example, so for example, so it means the XOR, so it's exclusive OR, and then the structure of exclusive OR is like this, and then format is the R format, and this is the name of instruction. Okay, then so any question about the RISC-V instruction? Okay, so then let's see how our high-level language code is translated and executed by a processor. Okay. You remember this? Okay. So I already explained. So we write a code using high-level language code. So this is the example of high-level language code in C. Okay. So and then using a compiler, then compiler translate our high-level language code into assembly language code. But its compilation, okay, its compilation is determined by ISA. So what does that mean? In order to compile our high-level language code, we need to select the target compiler. So in this course, we are learning about the RISC-V ISA. So which means that in order to compile this high-level language code into assembly code of RISC-V, then we need to use RISC-V compiler. Okay. It's the same the language translator. So we can translate our Korean to English or Korean to Spanish. So we need to select the different translation option, right? So it's the same to the compiler. So if we want to generate the RISC-V assembly code, then we need to use RISC-V compiler. And then if we want to generate x86 assembly code, then we need to use x86 compiler, right? Obviously, right? So using the RISC-V compiler, then we can generate the assembly code from this high-level language code. So in this example, so you can find some lines of code. So if you see this part, you can find that these names can be found in the RISC-V green card. Okay, so for example, so this is the add instruction. Where is the add? Or add is here. Okay, right. Then also you can find the is instruction, the RISC-V ISA document, or you can find these instructions in RISC-V green card. Actually, one line of this code represents the one instruction. Okay. So a processor, RISC-V processor receive one line of instruction, and then based on the definition of this instruction, then a processor will generate out the change of states. So for example, it received the add x6, x10, x6. Then processor read data from the x10 and x6, and then perform add operation, generate result. The result is stored in x6, and that's it. So operation by this add instruction is performed by processor. But you can say, so I said that a processor can only understand digital signals, right? But in this example, you can find English letters, not for digital signal. Right? Right? So using an assembler, then actually his assembly code need to be also translated into the machine code. Okay? Like this one. Oops, this one. So machine code is composed of many ones and many zeros. So it's the signal. Actually, it's line of instruction like add x6, x10, and x6 is translated into this machine code, what machine instruction. So actually, RISC-V CPU, the hardware CPU, can understand only this data, not this data. So it means that we have to make our program understood by our processor, and we need to translate our high-level language code into the machine language code composed of digital signal. Okay, understand? And then where is this code? So if we write the code, and then if we store our high-level language code in our computer, then we can find our code in storage system, right? So as a file, right? Like the hello.c. And then actually hello.c cannot be executed by a processor, right? So in order to execute our hello.c, then is hello.c into translates into the binary code. And then this actually machine code, and then this compiled machine code is called of binary, one binary file, right? It's called a binary. So inside of a binary file looks like this. There are many zeros and ones, essentially. So you can find the strange characters in our binary file if we also go to the binary file. Then, but actually, binary file includes the many zeros and many ones. Okay, it's machine code actually. Then, where is this binary? Where is this machine instruction in our binary file? So also binary file is a binary file. Actually, binary file is in our storage, right? But when we execute this binary file, then this binary file is transferred to the main memory, RAM of our computer system, and then this data, these instructions are read by a CPU, and then CPU read is instruction, machine code instruction, and generate result. Okay, generate out the speed of changing, right? So what I want to say is that actually we can find our binary file or machine code in main memory. Okay, so our binary code is stored in our storage system as a file, but enough to execute our binary file, then this file needs to be transferred to the main memory. And then also the content of the binary file looks like this. Any zeros and any ones. Then processor reads this data from binary file from the main memory and then execute instruction. So for example, if this line of code is read from the memory and then executed by a processor, then processor just generate the result of n as 6, as 10, as 6. You understand? So you need to remember that our code, our binary code, the machine code is stored in memory, and then it's read by a processor. This program mode is called the stored program. Stored program. So it means, so actually we can say that we just already know that we require memory to store our data, right? Like our text file data, or movie file data, or our database data. We can say we just think that we require memory in order to store our data. But how about the instructions? Our instruction, machine code instructions look like this. And then actually it is similar to binary data. You understand? Our data, such as the book file, or some image file, or video file, actually this data includes digital data, so digital signals like 0 and 1, right? Also, our instructions can be also represented as digital signals like digital data. So what I want to say is that in our memory, the computer memory, we can find instructions, also we can find data. Okay? And then stored program means that instructions and our normal data can be stored in the same place, same main memory. And then we can access this data using address. Right. In order to access data in memory, then we need to set address for the target data. Then using this address, we can access data in the memory. So it means enough to read instructions in this main memory. Then we also require address. Okay. So using this address, then we just set the address for the target instruction. And then a CPU read instruction from memory, and then this instruction is executed. This is the stored program model. Okay, actually, you need to understand this concept. Then the next class, I will explain the example of stored program. Okay. Okay. Any questions? Thank you for your attention. Then see you in the